Part 1. Biocosmology. Why life may belong to the universe. When we look out into the universe, life does not seem obvious. What we see first is darkness, immense distances filled with near-perfect vacuum, stars scattered like distant sparks, galaxies colliding, radiation flooding space, explosions powerful enough to erase entire solar systems. From this perspective, life appears fragile, almost misplaced, a rare anomaly surviving against overwhelming odds. And yet, life exists, not just as simple chemistry, but as awareness, as memory, as curiosity, as a system capable of asking questions about its own origins. This contrast lies at the heart of biocosmology. Is life an accidental byproduct of an otherwise lifeless universe? Or is life a natural outcome of the universe's deepest structures? For centuries, human thought leaned towards separation. Physics explained matter and forces. Cosmology explained space and time. Biology explained organisms. Life was treated as something that appeared late, local, and isolated. Biocosmology challenges this view. It proposes that life is not separate from the universe's evolution. It is embedded within it. The same laws that form galaxies may also give rise to cells. The same principles that organize matter into stars may organize chemistry into living systems. If this is true, then life is not an exception to cosmic history. It is one of its expressions. To understand this idea, we must abandon the image of the universe as a static container. The universe is not an empty stage on which events happen. It is an active, evolving process. From the first moments after the Big Bang, the universe has been changing in one clear direction, from simplicity toward complexity. In the beginning, matter was nearly uniform. Energy was evenly distributed. There were no structures, no chemistry, no boundaries. This state was lifeless, not because life was forbidden, but because complexity had not yet emerged. Life does not arise from uniformity. It arises from differences. Differences in temperature, differences in energy, differences in chemical potential. As the universe expanded, it cooled. Cooling allowed particles to bind. Protons and neutrons formed nuclei. Electrons joined them. Atoms came into existence. This was the universe's first act of memory. Atoms retain information about their structure. They are stable patterns that persist through time. Stability is essential for life. Without stability, information cannot survive. Without information, complexity cannot accumulate. Gravity then amplified tiny irregularities. Slightly denser regions pulled in more matter. Matter attracted matter. Gas clouds formed. Stars ignited. This process was not random chaos. It was organized growth, driven by physical law. Biocosmology views gravity as a creative force, not merely destructive. Without gravity, matter would remain diffuse forever. Without concentration, chemistry would remain trivial. Stars introduced a new ingredient into the universe. Sustained energy flow. A star is not just a glowing object. It is a system that maintains structure by balancing opposing forces. Gravity pulls inward. Nuclear fusion pushes outward. This balance allows stars to shine steadily for billions of years. Life requires this kind of patience from the universe. Short-lived energy bursts are not enough. Life needs time to experiment, to assemble molecules, to break them apart, to try again. Stars provide that time. Inside stars, simple elements fuse into complex ones. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen. Heavier elements follow. When massive stars die, they scatter these elements across space. Every carbon atom in your body was once inside a star. Every oxygen atom you breathed was forged in stellar fire. Life is not merely supported by stars. It is made of them. Biocosmology begins here, with the recognition that biology is built from cosmic processes. But material alone is not enough. Life also requires environments where complexity can persist. Planets provide such environments. A planet is a memory system. Its geology records billions of years of change. Its atmosphere stores chemical history. Its magnetic field protects delicate structures. Earth did not suddenly become alive. It became increasingly complex. Oceans formed. Chemistry diversified. Molecules interacted repeatedly. Networks emerged. There was no sharp boundary where non-life suddenly turned into life. There was a gradual increase in organization. Biocosmology emphasizes that life is not a moment, it is a continuum. Before cells, there were molecular systems capable of maintaining structure. Before genetics, there were chemical cycles. Before metabolism, there were energy gradients. Life is organized matter that learned how to persist. Persistence is the central theme. In physics, systems naturally drift toward disorder. Entropy increases. Life appears to resist this trend. But this resistance is local and temporary. Life maintains order by exporting disorder outward. This is not a violation of physical law. It is a direct consequence of energy flow. Stars export energy. Planets absorb it. Life uses a fraction of that flow to build structure. Biocosmology places life within thermodynamics, not outside it. Wherever energy flows steadily through matter, complexity can arise. This expands the range of possible life-bearing environments. Life does not require sunlight specifically. It requires gradients. On Earth, deep ocean vents support life without light. Chemical differences alone are sufficient. Elsewhere, life could be powered by different gradients. Chemical reactions, magnetic fields, tidal forces, radiation interacting with matter. Biocosmology does not ask whether alien life looks like us. It asks whether organization can persist. The universe offers countless environments where this may occur. Not everywhere, not always, but repeatedly. This challenges the idea that life is incredibly rare. Life may be rare per planet, but the universe contains billions of galaxies. Each galaxy contains billions of stars. Many stars have planets. The universe runs an enormous number of parallel experiments. Most fail, some succeed. Earth may not be special because it hosts life. It may be special because we are here to notice it. This leads to a profound shift in perspective. Humans are not outsiders in a hostile universe. We are products of cosmic evolution. Our bodies are composed of ancient matter. Our chemistry follows universal laws. Our minds emerge from physical processes shaped by time. We are something the universe does. Biocosmology reframes the question of meaning. If life is a natural outcome of cosmic processes, then existence is not an accident. It is a consequence, not planned, not designed, but permitted. The laws of physics allow complexity to grow. They allow memory to form, they allow systems to evolve. If the laws were slightly different, atoms might not bind. Stars might not form. Chemistry might be shallow. In such a universe, life would be impossible. Our universe sits in a narrow range where structure is possible. This is sometimes called fine-tuning. Biocosmology does not interpret this as intention. It interprets it as condition. Only in such a universe could observers exist to ask the question. Life does not require purpose from the universe. It only requires opportunity. And opportunity arises naturally. The universe is not alive in the biological sense. But it is generative. It creates structure. It creates patterns. It creates systems capable of persistence. Life may be the most complex pattern the universe has produced so far, but it may not be the last. Understanding where life is most natural requires understanding the universe's tendency toward organization. This is not a story that begins on Earth. It begins with matter learning how to remember, how to persist, how to resist a solution long enough to matter. In the next part, we will explore how entropy, information, and time interact to push matter toward living systems. We will examine whether life is simply one stage in a much larger cosmic process, and whether the universe has been quietly preparing for life since its very first moments. Part 2. Biocosmology. How time and entropy prepare life. Life does not emerge only from matter, it emerges from time. Without time, complexity cannot accumulate. Without duration, chemistry cannot experiment. Without persistence, organization collapses before it matters. Biocosmology places time at the center of life's possibility. In the early universe, everything happened quickly. Expansion was rapid, temperatures were extreme, reactions occurred at enormous energies. This was not an environment where life could exist, not because life was forbidden, but because it was premature. Life requires patience from the universe. As the universe expanded, it slowed. Cooling created stability. Stability allowed memory. Time transformed the universe from a violent furnace into a laboratory. This transition was not sudden. It unfolded gradually over billions of years. Biocosmology emphasizes that life is not a miracle that interrupts physics. It is a result of physics operating over long durations. The universe needed time to learn how to hold structure. Atoms were the first successful memory units. They resisted decay. They maintained identity. Molecules extended that memory. They stored patterns in bonds and shapes. But memory alone is not enough. Life also requires change. A perfectly stable universe would be lifeless. Nothing would evolve. Nothing would adapt. This is where entropy enters the story. Entropy is often misunderstood as pure disorder. In reality, entropy measures how energy spreads. The universe moves towards states where energy is more evenly distributed. At first glance, this seems hostile to life. Life depends on structure. Entropy erodes structure. But biocosmology reveals a deeper relationship. Entropy does not prevent local order. It enables it. Local order arises precisely because energy is flowing from concentrated sources to diffuse sinks. Stars burn. Planets absorb. Space cools. Between these stages, complexity can grow. Life exists not despite entropy, but because of it. Life feeds on gradients created by entropy's progress. As long as energy flows, structure can form temporarily. This temporary nature is essential. Nothing in the universe is permanent. Not stars, not planets, not life. Persistence does not mean immortality. It means lasting long enough to matter. Biocosmology reframes life as a transient but natural phase in cosmic evolution. Time and entropy together create a narrow window. Too little entropy change and nothing happens. Too much and everything dissolves. Life exists in the balance. The universe did not rush through this balance. It lingered. This lingering is critical. Many cosmological models show that if expansion were slightly faster, structure would not form. If slightly slower, the universe would collapse too early. Our universe unfolds at a pace that allows complexity to accumulate. This pace is not tuned for life. Life is tuned to this pace. Biocosmology shifts causality. The universe does not adjust for life. Life adapts to the universe. This adaptation depends on information. Information is the bridge between physics and biology. In physics, information describes how a system can be arranged. In biology, information describes how life persists and replicates. At their core, these are the same concept. Information is structure that resists erasure. A crystal holds information in its lattice. A planet holds information in its layers. A genome holds information in sequences. Life is matter that learned how to store information efficiently. But information must be copied to matter. This introduces a new requirement. Repetition. Life depends on cycles. Day and night, seasons. chemical reactions repeating again and again. Time provides repetition. Without repetition, there is no learning, no selection, no evolution. The early Earth offered cycles everywhere: ocean tides, volcanic activity, temperature fluctuations, chemical gradients. These cycles allowed molecules to interact repeatedly. Most interactions failed. Some persisted. Persistence is selection. Biocosmology sees natural selection not as a biological invention, but as a universal principle. Systems that last continue. Systems that do not disappear. This applies to stars as much as cells. Stars evolve. Some burn steadily. Some explode early. Planetary systems evolve. Some remain stable. Some collapse. Life follows the same pattern: variation. Persistence, selection. Evolution is not unique to DNA. It is a property of time acting on structure. Biocosmology therefore views life as evolution operating on chemistry. This perspective removes the sharp boundary between living and non-living. There is only increasing organization across time. The universe does not jump from physics to biology. It flows. One structure leads to another. Particles to atoms, atoms to molecules, molecules to networks. Networks to metabolism, metabolism to cells. At no point does the universe break its own rules. Life is not a violation. It is compliance at high complexity. Time also introduces fragility. The longer a system exists, the more it is exposed to disruption. Radiation breaks molecules. Impacts destroy environments. Stars change over time. Biocosmology asks not only where life can form, but where it can persist. Persistence requires protection. Planets with atmospheres, magnetic fields, stable orbits. These are not luxuries, they are filters. Life may form often, but it survives rarely. This may explain why intelligent life appears scarce. Complex life requires long, uninterrupted time, billions of years without total reset. Earth experienced mass extinctions, but none erased everything. Each reset reshaped life without ending it. This resilience is remarkable, but it is not miraculous. It is statistical. Across cosmic scales, some planets avoid total sterilization. We may live on one of them. Biocosmology does not imply that life is everywhere. It implies that life is not forbidden. The universe allows it where conditions align. Time is the quiet hero of this story. Without long durations, nothing meaningful emerges. Human impatience makes life seem rare. Cosmic patience reveals it as natural. From the universe's perspective, billions of years are brief. Stars live for billions of years. Galaxies for trillions. Life's timescale fits comfortably inside cosmic time. This alignment matters. If stars burned out too quickly, life would fail. If planets changed too violently, complexity would reset. Our universe offers extended calm between catastrophes. Not perfect calm, but enough. This balance shapes where life is most natural. Regions of the universe with excessive violence may be hostile. Regions with insufficient chemistry may be barren. Between these extremes lie habitable histories. Biocosmology focuses on histories, not locations. A planet is not habitable because of where it is. It is habitable because of what has happened there over time. Life depends on story, on accumulated events, on preserved structure. In this sense, the universe is not just space. It is memory unfolding. Every structure is a record of past processes. Life is a record that learned how to copy itself. This may be the deepest insight of biocosmology. Life is not merely chemistry plus energy. It is history that continues itself. The universe produced stars. Stars produced elements. Elements produced chemistry. Chemistry produced memory. Memory produced life. This chain did not require intention, only time and allowance. In the next part, we will explore how different cosmic environments influence this process. We will examine galaxies, stars, and planetary systems as life-shaping contexts. And we will ask a crucial question. If life is natural to the universe, why does it appear so fragile? Part 3. Biocosmology, where life is most likely to emerge. If life is a natural outcome of the universe, then location matters, not because the universe favors certain places, but because different regions offer different histories. Biocosmology shifts the question from, is there life out there? To, where does the universe most gently allow complexity to grow? Life does not emerge everywhere. It does not need to. It only needs environments where energy flows steadily, chemistry can diversify, and time remains uninterrupted long enough for organization to persist. The universe is vast, but it is not uniform. Conditions vary dramatically from one region to another. Some regions are violent beyond endurance. Others are too quiet to support complexity. Life prefers neither extreme. It emerges in between. Galaxies themselves differ in how they shape the potential for life. At the centers of large galaxies, conditions are extreme. Stars crowd closely together. Radiation levels rise. Supernovae occur frequently. In such regions, planets struggle to maintain stable environments. Atmospheres can be stripped away. Complex molecules are broken apart. Life may form briefly, but persistence becomes unlikely. At the far edges of galaxies, a different problem appears. Heavy elements are scarce. Stars form less frequently. Planets may lack the chemical richness needed for complex chemistry. Life requires more than hydrogen and helium. It requires carbon, oxygen, nitrogen, phosphorus. These elements are products of stellar evolution. They accumulate over time. Biocosmology highlights an important pattern. Life is more likely to emerge in regions that are neither too early nor too late in cosmic history. Too early, and the universe lacks chemical diversity. Too late, and stars begin to fade. Our galaxy appears to host a broad region where conditions are favorable. This region is sometimes described as a galactic habitable zone. But biocosmology treats this not as a strict boundary, but as a tendency. Life favors environments with balanced histories. Stars also play a critical role. Not all stars are equal when it comes to life. Massive stars burn hot and fast. They live millions of years, then they explode. They enrich the universe with heavy elements, but they do not provide stable energy for long. Life needs time. Very small stars burn slowly. Red dwarfs can shine for trillions of years. They offer stability, but with challenges. Their planets often orbit very close. Tidal locking becomes common. Radiation flares may be intense early in their lives. At first glance, such stars appear hostile. Biocosmology urges caution with first impressions. Life does not require comfort, it requires consistency. A tidally locked planet presents permanent gradients. One side faces the star. One side faces darkness. Between them lies a stable boundary. This boundary may offer a long-lasting environment with predictable energy flow. Such worlds could be favorable, not barren. Sun-like stars offer a different balance. Moderate lifespans, stable output, wide habitable zones. They do not dominate the universe numerically, but they offer familiar conditions. Biocosmology does not claim one star type is superior. It claims diversity increases probability. The universe explores many options simultaneously. Planets add another layer of variation. Life is more likely to emerge on worlds with surfaces or interfaces. Interfaces are crucial. Where solid meets liquid. Where liquid meets gas. Where heat meets cold. Interfaces create gradients. Gradients drive chemistry. On Earth, life emerged in water, but water itself is not the requirement. What matters is the ability of molecules to move, interact, and persist. Liquid environments are especially powerful because they allow constant rearrangement without immediate destruction. This makes oceans promising environments for life. But oceans need not be exposed to sunlight. Subsurface oceans beneath ice may be just as suitable. Moons like Europa and Enceladus contain liquid water beneath frozen crusts. They are warmed by tidal forces. Energy flows through their interiors. These environments are shielded from radiation. They are stable over long periods. Biocosmology treats such worlds as serious candidates for life. Life does not demand Earth's surface. It demands opportunity. Gas giant planets themselves may host unexpected complexity. While their upper atmospheres are turbulent, deeper layers may provide stable chemical niches. Life could exist as floating systems, adapting to pressure and chemistry. This challenges traditional definitions of life. Biocosmology is comfortable with that challenge. It does not seek familiarity. It seeks plausibility. Life also favors planets with protection. Magnetic fields deflect harmful radiation. Atmospheres regulate temperature. Stable orbits prevent extreme fluctuations. These features do not guarantee life, but they extend the window in which life can persist. Persistence is more important than origin. Life may begin often, it survives rarely. This may explain why microbial life could be widespread, while complex life remains scarce. Complex life requires not only origin, but continuity. Billions of years without total disruption. Earth experienced asteroid impacts, volcanic winters, and mass extinctions. Yet none erased all life. This sequence of near misses shaped complexity. Biocosmology emphasizes that complexity grows through survival, not perfection. Life adapts to damage. It incorporates history into structure. Planets that experience moderate stress may actually encourage complexity. Total calm produces stagnation. Total chaos produces extinction. Life thrives in tension. This tension exists across cosmic scales. Even the universe itself evolves under tension. Expansion pulls matter apart. Gravity pulls it together. This balance shapes the large-scale structure of the cosmos. Filaments form. Voids open. Clusters grow. Within these structures, stars and planets form. Life emerges within this cosmic architecture. Not at the center of everything. Not at the edges. In the filaments where matter flows gently. Biocosmology suggests that life is more likely in regions with long-term gravitational stability. Regions not frequently disturbed by massive collisions. Quiet neighborhoods within active galaxies. Life may also be influenced by cosmic events. Supernova enrich space with elements, but too many nearby can sterilize planets. Gamma ray bursts can strip atmospheres. These events are rare but devastating. Planets that avoid frequent exposure gain an advantage. Again, this is not design, it is filtering. Across billions of planets, some avoid catastrophe long enough for life to grow complex. We may be observing from one of those survivors. Biocosmology reframes the search for life as a search for histories, not snapshots. A planet is not defined by its current state. It is defined by what it has endured. Life is shaped by past conditions more than present ones. This makes detection difficult. A planet may appear lifeless today, but may host subsurface life invisible to us. Another may appear habitable, but lack the deep history required for complexity. Biocosmology encourages humility. Our criteria may be incomplete. Life elsewhere may not announce itself clearly. It may whisper through subtle chemical imbalances, through unexpected patterns. Understanding where life is most likely requires abandoning narrow expectations. Life may not be rare because the universe is hostile. It may be rare because persistence is difficult. The universe allows life to arise. It does not protect it. This has philosophical implications. If life is natural but fragile, then awareness is precious, not because it is unique in principle, but because it is difficult in practice. Every living system represents a long chain of successful persistence. Every conscious observer represents billions of years of uninterrupted history. Biocosmology does not diminish life's value by making it natural. It deepens it. Life is not special because it defies the universe. It is special because it cooperates with it for a very long time. Understanding where life is most likely to emerge helps us understand ourselves. We are not accidents. We are survivors. The universe did not intend us, but it allowed us. And allowance, repeated across time and space, becomes probability. In the next part, we will explore a deeper question. If life is natural to the universe, how does it transition from simple chemistry to complex intelligence? We will examine whether consciousness itself may be an extension of cosmic evolution, and whether the universe, through life, has found a way to observe itself. Part 4. Biocosmology, from life to awareness. Life is not the end of the story. It is a beginning. Once matter learns how to persist, the universe opens a new possibility. The possibility of awareness. Biocosmology does not treat consciousness as something added from outside. It treats it as a continuation of the same processes that created life itself. From particles to atoms, from atoms to molecules, from molecules to living systems. Each step increased complexity. Each step increased information storage. Each step increased the ability to respond to the environment. Awareness emerges along this gradient, not suddenly, not universally, but naturally when complexity crosses certain thresholds. Life responds to its environment long before it becomes aware of it. Single cells react to chemicals. Plants respond to light. Animals respond to movement. These responses do not require consciousness. They require organization. But as nervous systems evolve, something changes. Information is no longer only stored chemically. It is processed dynamically. Signals move through networks. Patterns emerge. Memory becomes internal. Biocosmology views nervous systems as information engines. They do not merely react. They model. A nervous system builds an internal representation of the world. It predicts, it anticipates, it learns. Awareness arises when a system begins to model itself as part of the environment. This is not magic, it is feedback. A system that monitors its own state gains a survival advantage. Self-reference improves adaptation. Biocosmology emphasizes that awareness is not binary. There is no single moment where non-aware life becomes aware. There is a spectrum. Simple nervous systems process simple patterns. Complex nervous systems process complex ones. Human consciousness is not a new category. It is an extreme point on a continuum. This reframes a long-standing question. Why did consciousness evolve? The answer may be simpler than expected. Because it works. Awareness allows prediction. Prediction allows planning. Planning allows persistence. In an uncertain universe, foresight is valuable. The universe does not reward awareness intentionally. It filters outcomes. Systems that adapt better persist longer. Consciousness may be rare, not because it is impossible, but because it is expensive. It requires energy. It requires stable environments. It requires long developmental times. Only a small fraction of life ever reaches this level of complexity. But given enough time and opportunity, some will. Biocosmology suggests that intelligence is not an anomaly. It is a potential. Whether that potential is realized depends on history. Earth experienced long periods of stability. Oceans remained liquid. Climate fluctuated but recovered. These conditions allowed complex multicellular life to evolve. With multicellularity came specialization. Cells differentiated, functions separated. Nervous tissue emerged as a way to coordinate complexity. Coordination increased efficiency. Efficiency favored survival. This chain of cause and effect does not require intention. It requires only selection, acting on variation. Awareness is a solution discovered by evolution. But awareness also changes the rules. Once a system becomes aware, it can modify its environment intentionally. This creates a new feedback loop. Life no longer only adapts to the universe. It begins to shape it. This is a critical transition. Biocosmology considers this moment a turning point in cosmic evolution. For the first time, matter influences its own future deliberately. Technology is an extension of this process. Tools extend the body. Language extends memory. Culture extends evolution. Human civilization represents a new layer of complexity. Information is no longer stored only in genes. It is stored externally: books, digital systems, signals traveling at the speed of light. The universe has begun storing information outside of biology. This raises a profound question. Is intelligence merely a phase, or is it a stable outcome? Biocosmology does not assume intelligence is permanent. Just as stars burn out, civilizations may collapse. Awareness does not guarantee survival. It only increases options. The universe does not protect intelligence. It tests it. Intelligent life must learn restraint. Energy use must remain balanced. Environmental stability must be maintained. A civilization that destabilizes its own planet may not last long. This fragility may explain the apparent silence of the universe. Advanced civilizations may be rare, not because life is rare, but because persistence at this level is difficult. Biocosmology does not rely on speculation alone. It extrapolates from patterns already observed. Complexity increases gradually. Thresholds are crossed rarely. Collapse is common. This pattern applies to stars, ecosystems, and civilizations alike. Awareness introduces a new responsibility. A conscious system can foresee consequences. This ability may determine whether intelligence survives. The universe may produce many intelligent species. Few may endure. From a biocosmological perspective, this is not pessimism. It is realism. The universe is not cruel. It is indifferent. Indifference allows freedom. Freedom allows both creation and destruction. Awareness amplifies both. There is another implication. If consciousness arises naturally from complexity, then it may arise elsewhere. Not identically, not with human emotions, but functionally. Other intelligences may process reality differently. Different senses, different timescales, different priorities. Biocosmology cautions against anthropocentrism. Intelligence elsewhere may not build radios. It may not explore space. It may remain quiet. Silence does not imply absence. It implies difference. This reframes the question of contact. The universe may already be full of awareness. We may simply be unable to recognize it. Even on Earth, intelligence exists in many forms. Octopuses, corvids, cetaceans. Each represents a different solution. The universe likely explores many such solutions. Awareness may be a recurring theme, not a unique event. Biocosmology connects awareness back to its origins. Consciousness is not a gift from outside physics. It is physics operating at extreme organization. Neurons obey physical laws. Signals obey chemistry and electricity. Yet the result is experience. This is not a contradiction. It is emergence. Emergence does not mean illusion. It means that new properties appear at new levels of organization. Wetness emerges from molecules. Life emerges from chemistry. Awareness emerges from networks. None violate the rules below them. They build upon them. This perspective dissolves the mystery without removing the wonder. The universe did not wake up suddenly. It gradually became capable of reflection. Through life, it began to sense itself. Through awareness, it began to question itself. Biocosmology does not claim the universe is conscious. It claims that the universe produces consciousness naturally. This distinction matters. The universe does not think, but it allows thinking to exist. In doing so, it creates observers. Observers change the universe simply by existing. They record, they remember. They interpret. Meaning enters the cosmos through awareness, not as an objective property, but as a relational one. Meaning exists where awareness exists. This may be the most radical implication of biocosmology. The universe did not begin with meaning. Meaning emerges with life and deepens with awareness. In the next part, we will bring all these threads together. We will ask whether life and awareness represent a temporary phase or long-term direction. We will explore whether the universe tends toward increasing complexity and whether biocosmology suggests a future where life and intelligence continue to expand. Biocosmology. Is life the universe becoming aware of itself? At the deepest level, biocosmology leads to a question that feels almost inevitable. If life arises naturally from the universe, if awareness emerges from life, then what role does awareness play in the universe as a whole? Is life merely a temporary pattern, or is it part of a larger trajectory? To ask this is not to claim intention, it is to examine direction. The universe has no goals, but it has tendencies. From the beginning, the universe moved from simplicity toward structure, from uniform energy toward differentiated matter, from particles toward atoms, from atoms toward stars, from stars toward planets, from chemistry toward life, from life toward awareness. This sequence is not guaranteed, it is not linear, it is fragile and often interrupted, but it repeats. Biocosmology asks whether this repetition reveals something fundamental. Complexity is not random noise. It appears in specific conditions, and when it appears, it builds upon itself. Life is one of those builds. Awareness is another. When awareness appears, something unprecedented happens. For the first time, a system within the universe forms an internal model of the universe itself. This is not metaphor. Brains simulate reality. They compress information. They predict outcomes. They imagine futures. A conscious being carries a version of the universe inside itself. In this sense, awareness is the universe folded inward, not symbolically, physically. Matter arranged in such a way that it can represent other matter. This is extraordinary, yet it emerges without violating any law of physics. Biocosmology suggests that this is not an accident layered on top of reality. It is a consequence of reality allowing information to process itself. Life is matter that persists. Awareness is matter that reflects. Reflection changes everything. Before awareness, the universe simply unfolded. After awareness, parts of the universe began to care about outcomes. Care is not a mystical force. It is selective attention. An aware system values certain states over others. Survival over extinction. Stability over chaos. These values shape behavior. Behavior shapes environments. For the first time, evolution becomes partially intentional. This does not break natural selection. It adds a new dimension to it. Selection no longer acts only externally. It acts internally as well. Choices matter. Biocosmology treats this as a new evolutionary phase. Not biological evolution alone, but cognitive evolution. Information no longer changes only through mutation and selection. It changes through learning. Learning accelerates adaptation. A species that learns can adjust within a lifetime rather than across generations. This is powerful, but it is also dangerous. Acceleration increases risk. Mistakes propagate faster. Technologies amplify consequences. Awareness magnifies impact. The universe did not design awareness to be safe. It allowed it to be possible. This brings us to the future. If life and awareness are natural outcomes of cosmic processes, what happens next? Does complexity continue to rise? Or does it collapse? Biocosmology does not promise progress. It recognizes cycles. Stars form and die. Ecosystems grow and collapse. Civilizations rise and fall. Complexity is always temporary, but temporary does not mean meaningless. A wave is temporary, yet it is real. Life may be a wave in the universe's history, a significant one. Awareness may be a crest. The universe may not be moving toward infinite complexity. It may be exploring it. Exploration does not require success. It requires possibility. From this perspective, the universe is not becoming conscious, but consciousness is becoming possible within it. That distinction matters. The universe does not need to awaken. It does not need purpose. Purpose emerges locally. Meaning is not embedded in space-time. It arises where awareness exists. This dissolves a long-standing tension. Meaning does not need to be universal to be real. It only needs to matter to someone. Biocosmology places meaning inside life, not outside it. This is both humbling and empowering. Humbling because the universe does not revolve around us. Empowering because meaning does not require cosmic permission. Life creates meaning by existing. Awareness deepens it by understanding. This reframes humanity's role. We are not the goal of the universe. We are one of its expressions. Not the first, not necessarily the last. Our responsibility does not come from destiny. It comes from fragility. Awareness is rare not because it is forbidden, but because it is difficult to maintain. Complex systems are vulnerable. They require balance. They require restraint. They require cooperation. The universe does not enforce these traits. It tests them. Civilizations that fail to manage complexity may collapse. Others may persist longer. Biocosmology suggests that long-term survival may require alignment with cosmic conditions. Energy use that respects limits. Technologies that preserve stability. Cultures that value continuity. These are not moral claims. They are structural ones. A system that destabilizes its own environment removes the conditions that allow it to exist. The universe does not punish such systems. It simply continues. From this view, the silence of the universe becomes less mysterious. The absence of obvious signals may not mean absence of life. It may mean brevity. Intelligent phases may be short compared to cosmic time. They may flicker and fade. Some may choose quiet persistence over expansion. Others may never reach technological stages we expect. Biocosmology cautions against assuming universality of human trajectories. Awareness elsewhere may not resemble us. It may not communicate. It may not explore. It may be inward-focused, or slow, or transient. The universe does not standardize outcomes. It experiments. Even on Earth, awareness takes many forms. Human consciousness is one configuration among many. This diversity suggests that awareness is flexible. It adapts to context. Elsewhere, awareness may arise under different conditions, different sensory worlds, different timescales, different values. Recognizing this expands our imagination. Life is not a single story. It is a family of stories. Biocosmology unifies them under one framework. Life emerges where complexity persists. Awareness emerges where information processing becomes rich enough to model reality. Beyond that, outcomes diverge. This framework avoids extremes. It does not reduce life to accident. It does not elevate it to destiny. It treats life as natural but not guaranteed. This balance is essential. If life were inevitable, it would be unremarkable. If it were impossible, it would be irrelevant. Life exists in between, rare enough to matter, common enough to be natural. This may be the universe's most elegant feature. Biocosmology also reshapes how we view ourselves emotionally. Existence does not need cosmic endorsement to be meaningful. We are meaningful because we experience. We are valuable because we can care. The universe does not care, but it allows caring to exist. That allowance is enough, from stardust to cells, from cells to minds, from minds to questions. This chain does not require belief. It requires observation. You are made of ancient matter. Your thoughts are physical processes. Your awareness is a pattern maintained by energy flow. And yet, you experience wonder. That wonder is real. Biocosmology does not strip mystery away, it relocates it. The mystery is not why life exists. The mystery is how often the universe manages to hold complexity long enough for awareness to bloom. Every conscious moment represents a victory over entropy. A brief one, but meaningful. The universe may never know itself as a whole. But through life, parts of it do. Through awareness, the universe gains perspective. Not globally, locally, and that may be the only way perspective can exist. Life does not complete the universe. It adds a layer. Awareness does not explain the universe. It asks questions about it. Biocosmology leaves us with no final answers, only a coherent story. A universe that unfolds according to simple laws. A universe that allows structure to grow. A universe that permits life. A universe that tolerates awareness. Within that universe, meaning is not imposed. It is created by living systems, by thinking systems, by observers who choose to care. You are not outside this story. You are inside it. You are not separate from the universe. You are one of its ongoing processes. Life may not be the universe becoming aware of itself in a literal sense, but life is the universe discovering that awareness is possible, and that discovery may be one of the most remarkable outcomes of cosmic evolution, not because it was destined, but because it happened at all.